to this very first EMSOFT session, which is on memory and compilers. I am Heiko Falk, and it's my pleasure to chair this session. Before going into the technical presentations, it is my duty to remind you that this session will be recorded via Zoom, so if you don't like it, you are welcome now to leave the Zoom room. Okay, our first talk will be entitled iNVMFS, an efficient file system for NVRAM-based intermittent computing devices. And presenter will be Ying-Jan from National Yang Ming Chiao Tung University. She received her master's degree from the Institute of Computer Science and Engineering of this university in Taiwan, and her research interest is on system software design for deeply embedded devices. Ying-Jan, please share your screen with us, and the floor is yours.
Okay. Can everyone see the screen?
Excellent, thank you.
Okay, good afternoon, everyone. Today, I'm going to introduce you iNVMFS, a file system designed for NVRAM-based intermittent computing devices, and Ying-Jan from National Yang Ming Chiao Tung University. Due to the large size of the battery, many sensor-scale devices are not developing toward batteryless and energy harvesting. Energy harvesting means device can get energy from the environment, like sunlight and wind. However, these energy sources are not stable, so the devices encounter power failures frequently. This can incur the loss of the computation progress. Therefore, we use intermittent computing to cope with this issue. Intermittent computing using fine-grained checkpoint to preserve as much program progress as possible. Let's see the figure. The green points are checkpoints of different timing, and the red points are power failures. Because checkpoints set program state to the persistent memory, so we can recover the state when the power fails, and the device can resume its execution. With NVRAM, the cost for saving program states decreases. Here we use FRAM because of its ultra-low power feature. After introducing intermittent computing, we move on to the reason why sensor devices require a local storage for data processing. This is because near data processing is strongly demanded in edge computing. With local storage, sensor devices can achieve faster response and energy saving. Here's an example of what would happen with only program state protected. When the file is created, a node block is generated at the same time, and one checkpoint is committed as T1. Then we write the file data, and user data block U1 is chosen and marked as used in BMap. At this time, power fails, and N is not connected to U1 after restoration with the latest checkpoint. The program restarts to write file data again. However, U1 is marked used in BMap, so another user data block U2 is used. Then U1 becomes an orphan block. This is a severe issue because sensor devices have unstable power sources. To solve this problem, this work supports checkpoint for both program and storage state with a lightweight file system. Our file system has three goals. First, efficient checkpointing. Second, exploit byte addressability of FRAM. Third, use impress by writing whenever possible. The challenge is how to identify which data can be impress written. In the figure, the data before T2 is pre-checkpoint data. The data after T2 is post-checkpoint data. The pre-checkpoint data may be used in the restoration procedure when power fails, so they must not be modified. By contrast, the post-checkpoint data are not needed in restoration, so it might be safely overwritten like the undefined space. Take a look at the architecture of iNVMFS. We divide data into two parts, metadata and user data. In the metadata part, we have a location bitmap, no blocks and directories. Because their access size is much smaller than a block, byte level logging is adapted for them. And block copy on write is used for user data. Both metadata and user data can use impress by writing if possible. How is the writing policy designed? It's utilize the concept that most sensor devices generate the behavior of small file appending. Take a weather information recording sensor, for example. It keeps appending new weather information into storage instead of updating them. Post checkpoint data and undefined spaces are probably overwritten. However, identifying all post checkpoint data incurs higher overhead. The green data here are all post checkpoint data. To identify this data, we need to keep their offsets and lengths. Thanks to the small file appending behavior, the region from checkpoint to end of file are seldomly updated, so we can treat them all as post checkpoint data. There are three kinds of post checkpoint data: metadata, existing log, and user data. Metadata is usually updated with byte logging. Impress by writing is utilized when the metadata existed in a log. User data is updated with block copy on write. As previously mentioned, sensor device hardly update existing user data. For undefined space, impress writing is adopted because it contains no meaningful data. Two examples for write operation are shown here. The blue box are pre-checkpoint data. The red phones are post-checkpoint data. The gray box are undefined space. The first example is file creation. This flow involves several steps. Find the node block of the directory. Build a pointer to the new file. Because the pointer belongs to post-checkpoint data, we write this change into log space. Then we use bitmap to get an empty node block. Also, bitmap update is post-checkpoint data, so we add a log for it. The node block obtained from the bitmap is undefined space, so we can override this region directly. The second example is to append data. If a node block contains data, new data is appended to end of file, which is also undefined space. Therefore, we can override this region directly. At the same time, file length increases. The length is post-checkpoint data, so we add a log rate to record list. Length change if we repeatedly append data to this file. No new log is generated because we choose to do impress byte writing on the length log. This flowchart puts all things together, and we won't go into details. The right of this chart describes all of the write operation. We can see that the most of the write are byte level writing with lower overhead. Only updating existing user data incurs block copy on write, but this behavior barely happens in sensor devices, so the write overhead of this file system is greatly reduced. Here we talk about the checkpoint commit and restore. Commit include two steps: flush the dirty data in volatile caches, and turn all post-checkpoint data into pre-checkpoint data. The space of the deleted data is released only after the committed logs are written back to the storage. This is because the delete operations are also recorded in the logs. Restore is fast and simple as the figure shows. We only need to move the log tail to discard all the post-checkpoint log. Lastly is the experiment. Here are comparisons with copy on write and LFS. They are common file systems supporting checkpoint, we designed 5 workloads based on the related work and our analysis on sensor behaviors. The left figure, the y-axis, is total execution time. Compared with copy on write and LFS, our iNVMFS reduced total execution time by 70% and 84%. The reason are iNVMFS mostly handle write operation through the byte level writing instead of block level copy. Copy on write will copy a full block when the first update, and it also suffers from the wandering tree issue. LFS needs 2 full block writes for no block and user data block, even though a small data is written. Obviously, our iNVMFS can incur much less overhead for sensor devices compared with the block-based copy method, copy on write and LFS. The right figure shows the energy consumption with the same setting. The trend is similar to that of total execution time. iNVMFS is a checkpoint set, EMSOFT-based file system for energy harvesting devices. Its concept is to utilize the input by writing as much as possible. Local metadata, post-checkpoint data, and undefined space are the targets to do in-place writing. What does it achieve? Compared with copy on write and LFS, it reduced the total execution time and energy consumption by 74% and 73% on average. In addition, this paper is the first study on file system supporting for NVRAM-based intermittent computing to the best of our knowledge. And now, more and more design adopts large capacitor or supercapacitor. We believe that the sensor devices will become more capable of running file system. At the same time, is the trend and the goal of the future sensor device. Here is the end of my talk today. Thank you all for listening.
All right, thanks a lot for this interesting presentation. So we have time for a couple of questions. Are there some questions from the audience locally in Shanghai? Otherwise, if there are questions from the virtual audience, then please put them in the chat or raise your hand in the Zoom tool. I have a question regarding the applicability of your file system. Especially, flash memory is the dominating technology for permanent storage in embedded devices. And if you talk about in-place writing and byte level writing, then I was wondering in how far this is applicable for flash. Yeah? Flash cells can only be updated in a block fashion, and you can only write a flash memory cell a couple of thousands of times. So how does your approach relate to these limitations of flash memory?
We can see the picture over here. This is a SSD. And now SSD is a common storage for embedded system, but the NVRAM, the byte addressability RAM is also more popular now, and it becomes more and more cheaper. And we believe the trend is the non-volatile RAM will be the common storage for the embedded device. And we can see in the picture, the SSD has the higher latency under the certain throughputs. And the Intel update now is not supporting now, but it has the lower latency compared with the flash-based SSD. And traditional like a traditional method like copy on write and LLFS works on the broad-based storage like SSD, but we want to propose the non-maritime methods for the embedded system. Thanks.
Okay. Thank you. We also see a comment there in the chat from one of the co-authors. Yeah. Okay. Thanks a lot for this clarification. Are there other questions from the audience? If not, then I would like to stick into our time schedule. Thanks a lot, Ying-Jan, for your presentation. And this way I would move on to our second presentation today. It is entitled Mercury, Instruction Pipeline Aware Code Generation for Simulink Models. Presenter will be Zehong Yu from Tsinghua University. Zehong Yu received the bachelor degree in software engineering from Southeast University in 2021. He is pursuing now a master's degree in software engineering at Tsinghua University in Beijing. His research interests are in the areas of model-driven development and embedded software engineering. Please go ahead with your presentation. The floor is yours.
Hello, can you hear me?
Yes, perfectly. Thank you.
Okay, I share my slides.
Okay, go ahead. It seems that your microphone is not working. We don't hear anything. Now you are muted.
Okay.
Yeah, yes, now we can hear you.
Maybe. Can you hear me now?
Yes.
So that's my prepared video. So
now again, we don't hear anything. It seems that your computer mutes as soon as you move into the presentation mode.
Oh, okay. Can I share my prepared video for this? My computer's microphone have some troubles.
Can't you just show us your slides like this in this Microsoft PowerPoint window?
Okay. Maybe can you maybe the next one can you change the presentation sequence? I have some troubles.
Okay. All right. So let me ask Niccolò, who would be the third speaker. Could you step in and give your presentation right now?
Yes, I'm here. Just a second to start sharing.
Okay. Then, in the meantime, thanks a lot for being so flexible. The presentation that Niccolò will give is entitled An I/O Virtualization Framework with I/O-related memory contention control for real-time systems. Niccolò is a PhD student at the Real-Time Systems Lab on the School of Advanced Studies in Sant'Anna of Pisa. And Niccolò's research interests include the I/O virtualization, memory contention, and cybersecurity. Please, the floor is yours.
Can you see my screen?
Yes, perfectly, and we can also hear you.
Okay, thank you. Thank you for your introduction. This work deals with a novel I/O virtualization framework for real-time system that was developed with my co-authors of Reti's laboratory of Scuola Superiore Sant'Anna. Modern real-time systems, such as autonomous cars, require multiple I/O devices to interact with the environment. At the same time, such systems integrate many application domains with different levels of criticality on top of the same hardware platform. For this reason, today, a key aspect is virtualize such devices. However, when we talk of I/O virtualization, we must face against some challenges. In a real-time domain, the I/O virtualization mechanism must provide guarantees about the latency, while ensuring the integrity and confidentiality of the I/O data among different domains. Moreover, the control of the memory contention generated by such devices is important to guarantee system performances. This is a key aspect of this work that has never been addressed before. Typically, memory contention is considered only generated by simultaneous accesses of cores to global memory. However, in a heterogeneous platform, there are also many I/O devices that simultaneously access global memory and contribute to generate memory contention. To face with this issue, we design our virtualization framework following some design principles. First of all, we want to guarantee by design the safety and robustness of the virtualization mechanism to secure attacks. We want also to provide a way for measuring the real-time performance of the I/O using a bounded delay model. Moreover, this framework should be portable to other devices and platforms and allow the user to interact with the virtualized devices in a transparent manner. Finally, the I/O-related memory interference can be a big problem, and so this framework should provide a mechanism to explicitly regulate it. There exist many possible ways to access I/O devices in a virtualized environment. The two most common are virtualized pass-through, where virtualized devices are exclusively assigned to a single virtual machine. This minimizes the overhead introduced by the virtualization mechanism, but does not allow us to share the device among different virtual machines. The second option is the software device virtualization. This way, it's possible to share the devices among different guests. However, this requires to pay for extra overhead and higher latency. In this work, we use this second solution with a dedicated virtual machine called I/O virtual machine that take care of sharing the devices with an involved in virtual machine. But how to perform the inter-virtual machine communication? We use a wait-free ring buffer explicitly designed to guarantee predictable time to perform push and pop operation. Moreover, this algorithm was designed to keep safe the consumer, even if the producer corrupts the buffer, and vice versa. These buffers are stored in a memory region shared by the two virtual machines that needs to communicate. In particular, for each guest I/O device couple and for each needed direction of the I/O, we reserved one of such memory regions. Now, how to manage the I/O-related memory contention? ARM QS400 regulators are programmable hardware devices available in many system-on-chips. These components allow regulating the maximum memory bandwidth available for each device, thus controlling the I/O-related memory contention generated by the controlled devices. Well, now we have all the components we need to build our framework. Here you can see how the presented components combine to our virtualization framework. The I/O virtualization driver is an additional component that is required by each guest virtual machine to interact with the wait-free queues and expose the device interface to the user. To validate our framework, we wanted to focus on a high-performance modern device. For this purpose, we decided to virtualize the Gigabit Ethernet module of the Xilinx UltraScale Plus. In the considered case study, we use 3 virtual machines on top of the Claire hypervisor. The first one runs Linux, and the second one runs FreeRTOS. This choice was performed to show how our solution is cross-compatible in different OSs. The third guest is the I/O virtual machine, which shared the third core of the platform with the Linux guest. In this work, we used a round-robin scheduler to guarantee fairness and provide predictable latencies to all guests. Moreover, in addition to the Ethernet device, we considered also the low-power DMA to generate memory traffic interference. The considered platform provides several QoS regulators. In particular, we exploited the regulators of low-power DMA and Gem Ethernet, since are the main devices used in our settings. Using the presented setting, we analyzed the behavior of the virtualization from the first virtual machine. We measured both bandwidth and latency observed from this guest using iPerf3, which is a standard tool used to measure network performance. In the second guest, we used Packet to generate network packets to interfere with the I/O scheduler. Moreover, this machine was also in charge of configuring the low-power DMA to generate memory traffic in order to produce memory contention. We compare our solution with the state-of-art Xen hypervisor, since it's a widely adopted hypervisor in many domains, and its official support by the embedded platform used in this work. There are many possible configurations for the QoS regulators. During our research, we found a representative subset of such configuration that allow to understand the effects of QoS regulators on the system. We tested such configuration in 5 different scenarios that consider different network and memory traffic loads. Since Xen does not provide QoS regulation, in the last scenario, the regulation is applied only to our solution. Results achieved showed that already without network and traffic interference, our solution outperformed Xen both in terms of bandwidth and latency. This is possible because our framework is much lighter than Xen and thus introduces less overhead. Moreover, when the second guest starts generating traffic, our framework does not observe an increase in latency. This effect is even more clear when we greatly increase the network interference, since Xen network performance drops, while in our framework remains stable. This is thanks to the I/O scheduler fairness used in our framework. In these settings, we can clearly see how the memory contention introduced by the low-power DMA can dramatically affect the performances of the Ethernet device in both settings. However, thanks to the QoS regulation available in our framework, we are able to mitigate contention and restore the original networking performances. Well, but what are the effects of such QoS regulation? Adopting a strict QoS regulation allows reducing the memory contention generated by the regulated device. However, this reduces the memory bandwidth available for the device and increases its latency. Dually, a softer QoS regulation allows to increase the device performances, but also increases the memory interference. So it's important to find a trade-off between device performance and contention. Experiments show us that below a certain regulation value, the effect on memory contention becomes stable. So we can select the lowest regulation value to maximize the memory contention, and while minimizing the effect on the regulated device. Similar observation can be performed when we analyze the alpha-delta model of the system. We measured alpha and delta values both in the I/O virtual machine and the guest, and we observe a similar behavior. If we increase the QoS regulation with more than a given value, the performances of the regulated device becomes independent from the memory contention generated by cores and devices. Concluding, we demonstrated that our framework can virtualize I/O devices, achieving higher performances than state-of-art, and introduces a novel mechanism to deal also with memory contention to guarantee bounded performances. Future work will involve the study of other scheduling algorithms, the development of an automatic mechanism to configure regulators based on high-level performance requirements, and the study of the alpha-delta model considering multiple I/O devices. Thank you for your attention. There are some questions I will be pleased to answer.
Excellent. Thanks for your presentation. We have time for one question, maybe. Are there questions from the physical or virtual audience? If not, so let me ask you a brief question. You mentioned in the very beginning of your presentation that you strive for measurable real-time performance. However, I'm a friend not of measurements, but of analyzing real-time properties. Can you provide static guarantees that the bandwidths of your approach are at a certain level? Can you analyze your system statically?
Yeah, sure. We have performed alpha delta measurement using the alpha delta model I presented before. This allowed us to have guarantees on how the system behaves in different QoS regulation conditions. This way we can provide a way to configure such regulators to enforce a specific performance of the devices and so ensure a predefined high-level performance for the single guest virtual machine.
Okay, understood. Thank you. All right, keeping an eye on the clock, I would like to close this presentation. Thanks again to our second speaker. And I would like to move back or forth, depending on how you see it, to the presentation on Mercury, instruction pipeline aware code generation for Simulink models. Zehong, you will be the speaker. Are you ready for presentation?
Yeah. I'm ready. Sorry for the wasting your time, and thanks for the second speaker. Okay. Is my voice clear? Hello and welcome. My name is Zehong from Software Department of Tsinghua University and working with Zhuo and Professor Jiang. I would like to introduce the findings of Mercury and its pursuit of instruction pipeline aware code generation for Simulink models. The journey of an embedded developer can be difficult by passing Simulink. It is a widely used model-driven design environment and has become very popular in embedded scenarios, such as vehicle control system and autonomous driving and so on. Besides, it offers various toolsets such as model-based simulation, verification, and code generation to facilitate the development. State-of-the-art code generator employ various high-level optimization to generate high-quality code. Simulink embedded coder, one of the most widely used commercial tools, adapts optimizations such as local variable limitation to ensure the quality of the code. DFSynthesis, the most recent academic work, focus on generating more efficient code for models containing complex branch actors. However, these code generators overlook the potential of low-level architectures to optimize the performance of the generated code, especially the instruction pipeline. For example, Simulink embedded coder translates the model shown in the figure in the following steps. First, it obtains the data from input 1 and calculates the absolute value of it. Then it adds up the result of previous step with a const. After that, obtain data from input 2 to perform the corresponding math operation. Finally, combine the result into a vector output. However, in the generated code, it leads to a read after write hazard since the execution of line 4 should wait for the result in line 3, which introduce instruction pipeline stores. This can be avoided by swapping the translation order of the model actor. To generate pipeline-friendly code that decrease the instruction pipeline stores, we have to struggle with the following two challenges. The first is to construct a pipeline-friendly translation sequence of model actor, specifically when selecting actors for translation. There might be multiple available options. A slight difference in the selection may lead to a serious performance gap due to the instruction pipeline stall. Besides, the lack of processor parameters and other relevant information makes it harder to select the most suitable actor for translation. The second challenge is to maintain the semantic consistency between the translation sequence and the models to avoid for code generation, the most important thing is to ensure the semantic consistency. How to ensure semantic consistency in adjusting the translation sequence is important to note. The increasing complexity of the model and the rich semantics result in difficulties in collecting and analyzing data dependencies among actors. The goal of Mercury is to for utilizing instruction pipeline inside Simulink models to avoid unnecessary data headers. That's improving the execution efficiency of the generated code. The main idea is that for the actor for translation, it will not select its subsequent actor for translation, but the other actor without data dependencies. The status shown in the figure are obtained from Intel Win2 profiler. It shows that based on the optimization of Mercury, the execution time decreased by 26.1% compared with the original code generated by Simulink embedded coder. So let's move to our overall framework. In the first step, the design of Mercury mainly contain 3 steps. The first step named pipeline sensitive, we obtain the property of each actor and the data dependencies. In the second step named the critical actor identification, we obtain the candidate actors for selection. In the third step, we iteratively select the most suitable actor for translation and perform code synthesis for each actor in the translation sequence. So in pipeline sensitive content collection, we pass the given model into well-structured IR as the propagation. Then based on the IR, we obtain the necessary property of the actor, such as actor type, parameter, import and output, as well as data dependencies. Besides, for circular data dependencies, we break them by dividing the data delay actor into data storage and the data fetch actor. So in critical actor identification, based on the model actor library and actor property, we fetch the required instruction for executing the actor. And then we estimate the execution latency for each actor. After that, we adopt a topologic-based method to traverse data dependencies and obtain candidate actors for selection. In our third step, pipeline-friendly code synthesis, we apply the list of penalty priority to generate translation sequence. In each iteration, we select candidate actor with minimal penalty value for translation. And based on the execution latency, we update the penalty value for other candidate actors and the subsequent actors. And after selecting the suitable actor, we release data dependencies pointing from them. So let's take an example shown in the figure to better illustrate the process. The circular item present a model actor the green one represents a point. The green one represents a candidate actor, while the orange one represents an actor with penalty value. In each time, we select a green actor for translation and release data dependencies pointing from them. After that, we update the penalty value of the selected actor and turn in the color to green for the available for the candidate actors in the next selection. We iteratively repeat the above step until all the actors have been selected to form the translation sequence. We evaluate the performance of Mercury on 10 widely used Simulink models as well as an industry model to demonstrate the effectiveness of Mercury on different architectures. We conduct experiments on Intel and ARM machines with GCC compiler. Overall, compared with Simulink and DF synthesis, we achieved 10% to 33.4% and 9.2% to 59.4% improvement in terms of execution time, respectively. Besides, to evaluate the utility of Mercury, we compare Mercury with optimization implemented in GCC, compared with the code generated by Simulink. Mercury achieves better performance on 6 models, and compared with DF synthesis, Mercury still achieves superior performance. We also conduct experiment on on correlation coefficient between pipeline utilization with execution improvement. The statistics shows that Mercury actually works to improve the execution efficiency due to the improved pipeline slots utilization. That's my presentation. Thanks. Maybe they'll have some troubles.
All right. Thanks for this presentation. Are there any questions from the audience, please? Please put your questions in the Zoom chat or in the local auditorium. If they're in Shanghai, simply raise your hand to your local host. I was wondering a little bit, you know, I'm a compiler guy, and instruction scheduling and optimizing code for the pipeline is one of the crucial aspects that we do within compilers. And now I was wondering that you are trying to do this at a super abstract level during code generation. Why don't you think, or what makes your approach different from instruction scheduling within a compiler?
Okay. So in our findings, we find that in the model level, we can obtain some high-level data dependencies and easily rescheduling this instruction execution. And we also conduct our implemented optimization with optimization implemented in GCC, and the results shows that in some models we still get higher performance compared with GCC. So we think the high-level information contained in Simulink models can help we schedule the instruction better.
Okay, I understand. But instruction scheduling requires really precise knowledge about which machine instructions an actor in Simulink will execute and how often and what the latencies are. You need quite low-level information for the x86 or for the ARM architecture. How do you get that?
Right. We get that from two ways. The first is from conducted in experiments on several instruction latency from open source open source document, and then we also conduct experiment on of several instruction latency on the target machine by ourselves to get the latency.
Okay, good. Thanks a lot for your presentation, for your answer. I would then move on to our fourth and closing presentation in this first EMSOFT session. The final paper is entitled Toward Register Spilling Security Using LLVM and ARM Pointer Authentication. Andrea Fanti from the Politecnico di Torino will be the speaker. Please share already your screen with us. Andrea is a computer engineer who specialized in cybersecurity. He graduated in December of last year at the Politecnico of Torino with a master thesis about compilers and memory security. His work is in close collaboration with Huawei, and in his free time, Andrea can be found hiding in the woods or trying new receives, hopefully successfully also. Good. Now he's working as embedded software engineer at Silicon Labs. So, Andrea, we are looking forward for your presentation, please.
Thank you. Can you see my screen very well?
Yes, it works nicely.
Okay. So, hi, I'm Andrea, and today I will tell you about the paper I wrote with my colleagues, which is about register spilling security using LLVM and ARM pointer authentication. So, our work concentrated on memory security, and why? Because memory is often targeted in attacks, and this is why, because in the von Neumann architecture, memory is not aware of what it's storing, so it's not really secure. It's only executing instructions like take data at this address or store data at this other address. And we even have papers like eternal war in memory, because it happens often that some issues in memory are discovered, then a mitigation is developed and started to be used, and then another issue is found, and the cycle continues like this. So think, for instance, about code injection, return-oriented programming, and then data-oriented programming. Spills concerns memory security and often they are not considered, as we will see later. But first, what are register spilling? The compiler at some point during execution needs to decide where to store variables of each function, and it tries to store everything on registers because they are faster. But for instance, ARM CPUs only have 32 registers. So if at any point during execution we need to have more than 32 values at the same time, then often they are saved somewhere else. They need to be saved somewhere else. So the compilers generate additional instructions to store these values temporarily on the stack and later reload them when needed. Spill instructions in the case of ARM CPUs are basically store instructions, and reloads are the load instructions. There is also another type of spill, which is related to function calls. If a function uses any of these Kali saved registers, then as per procedure calling standard, we need to save them on the stack. That is, they need not to be modified outside of the function. But why are spills a security risk? Because when we are spilling registers on memory, there is an issue with the memory that an attacker can exploit to modify the spills before they are reloaded in registers. The program will not know that these values changed, so it will use them as if nothing happened. And you can think that this value could have been something important, like for instance, if it was a variable used to decide if a digital signature is valid or not. So there are some languages that support defining a safer portion of memory, but this is happening before compiler optimizations take place on the language specific side of the compiler. because usually compilation is performed in 3 steps in LLVM and all its supported languages, also in GCC. Basically, we convert first the source code in compiler internal representation, which is like an assembly, but for compilers. Then we optimize it into internal representation. And only then we convert this to specific assembly of the target or machine code directly. And another things to consider is that spills are very present in modern software. We analyze their presence in Chromium, which is the open source code base for Google Chrome. And we noticed we have over 1.5 million spills in its code base. We didn't find any particularly unsafe spills, but you have to admit that this is a very large attack surface. So we modified the LLVM ARM compiler to try to have some mitigation against these kind of attacks. And to do this, we use ARM pointer authentication, which was designed to embed MACs in pointers by storing them on the unused portion of 64-bit pointers. We actually use this particular instruction, which is PACGA, to generate a 32 bits keyed MAC. This instruction is taking 3 parameters and used to generate a keyed MAC for generic data. These 3 parameters are the modifier, data, and the data to sign and destination register. The modifier is to not always generate the same MAC with the same input data. And also there is a hidden 4th parameter, which is the key for the keyed MAC, which is not accessible at normal execution level. So we said that there are 2 kinds of spills, and this means 2 modifications to the compiler. And register pressure is when the compiler is running out of registers to allocate. This happens while generating code for a function during register allocation. So on the left here, you can see an hypothetical assembly program generated by the LLVM without our instrumentation. And on the right, there is the same portion of code with the instrumentation. So now what happens is that in parallel to the store instructions, to spill a register, we generate a MAC with PACGA and store it on the stack alongside the spill value. Once we reload the register, we also reload the MAC, recompute it from the reloaded data and see if it changed. If it changed, we have no way of reconstructing the correct value because MACs can only be valid or invalid. They cannot tell us which portion of data changed. So our only choice is to abort the execution of the program. The second cause for spilling is cohesive registers. And these are handled in the compiler during prolog epilog insertion stage, where the compiler prepares and appends instructions around each function to prepare the function code to be executed. For instance, here we also do allocation for the stack space in this stage of the compilation. But we care about cohesive registers, and in this case, we can compute a single MAC for all of them because they are spilled and reloaded all together. And so we can compute a single MAC at the beginning of the function when the registers are spilled on the stack, and then we recompute it again at the function end before returning. In this case, we can also speed up the MAC generation, and we do it in this way. So as you can see, we are basically using one register LV2 as a modifier for the next step by XORing it into the MAC computed so far. And considering that a single PACGA takes between 4 and 5 clock cycles, we are saving some time by executing 2 XORs instead of another PACGA. Our implementation also supports encryption. And with encryption, we are doing like a string cipher, basically. As an initialization vector, we are computing at compilation time and hash with the function signature, a combination of the function name, parameter type, and order, and return type. And at the same time, we also hash the frame index, which basically is the address of the spill slot. And then we trim everything out to 16 bits. This hash is used to see the string cipher. We are generating a 32-bit string initialization vector. At time with PACGA and sorting them to the registers. Because string cipher, you can guess that this process is quite slow because we are executing PACGA twice per register. But now you will see the analysis. So we analyze the performance of the code generated with the instrumentation. We compare it to a normal execution. And as code size, we have a 9% increase with only integrity protection, and instead of 28% increase with code size when we also have encryption. For execution time, we have 17% increase with only integrity protection and 104% increase with also encryption. We also expected a speed increase because for the solution, we are reserving 2 registers to generate and check the MAC, and this increases register pressure. But it was a bit of a surprise when we noticed only 0.2%. And we need to reserve 2 registers because to compare the MAC, once it is reloaded, we need to store both the reloaded MAC and the one computed from the reloaded data. So if we override the protected data while recomputing the MAC, an attacker could modify the register before it is reloaded again. But going back to data, you need to consider that these numbers are large, but we're protecting really all the spills in the program. So if you think about those 1.5 million spills that happen in Chromium, probably not all of them need this level of security. We, for instance, expect a future work to be restricting this protection to only variables declared as secure in the source code, and this modifier is kept in the compiler intermediate representation for the backend to use it for code generation. We also performed a security evaluation of our solution. So theoretically, we are using 32 bits of the whole 32 bits of the MAC, so no brute force is feasible. And also the encryption uses a different initialization vector every time, so there is no keystring reuse. Experimentally, instead we use Juliet, which is a program that tries to exploit itself. We executed the buffer overflow suit, and we saw that 23 tests out of 67 are not successful in the attack. And we consider this as a good result because we did not develop this feature for buffer overflow in NVM, but rather for speed protection in general. So, and this was also the end of the presentation, so you can find our contacts here. And if you have any questions, I will be happy to answer them.
Thanks a lot, Andrea, for this interesting presentation. Do we have questions from the audience? David, please.
Yes, thank you for a very interesting presentation. I was just wondering, also the connection. I mean, this sounds like a very general approach, and the connection to embedded systems and real-time systems. So, are there particular things that also affect this? For example, timing. So, do things become less or more predictable regarding timing, or are there other effects using this approach?
Sorry, I didn't get the question. So, so this thing slows down the execution time, but is predictable in a way that package A always takes the same time to execute. So everything is like, if you know how the code is compiled, you can know a priori how it will be affected at time. But for our measurements, basically we executed the spec benchmark, and then we did like an average of how this is affecting to calculate somehow an average of how it is affected normal execution of a program.
I think it answered my question about timing. Are they good? Thank you. Are there other aspects regarding memory that is also, should be considered when you're implementing this on an embedded system?
So the major problem is that we are using, I don't remember now if I showed. So it's difficult to know a priori how much more memory you're using, because basically you're using 64 bits more for each spill slot actually. So it could be that it's less than the spill count because the compiler tries to use less memory, as few memory as possible. So it tries to reuse stuff. If they are not together spills, it will use the same spill slot in the stack. So for that, you will need like an analysis of how much frequently functions are called and something like that. So like a dynamic analysis of the code, which is we didn't do actually. We just analyzed in the paper. You can see the analysis for the frame. So we did like a total of the analysis of all the functions, how much it increases with. So we did like okay, so we analyzed like the binary. Before it was at most allocating this much, all the functions together, and afterwards it was allocating this more. But you can also retrieve this data just by basically it's the same as the spill count, just mathematical operation.
Okay, thanks a lot. Thanks a lot.
Okay,
thank you for the question.
Quite a theoretical final question. You have these registers which contain the max in the end, and what if these registers also become subject to spilling and the max gets spilled out into the main memory onto the stack?
Okay, so in a way, yes. I mean, they cannot be spilled, but we are doing it on purpose, so they are spilled alongside the normal spills, but we are reserving them so that they don't get used for other purposes. But it's not a problem if they're spilled because it's a keyed MAC, so they are sort of protected by the key because the key is never spilled. The key is actually stored also in a register in the CPU, but it's a reserved register. So that PAC-GA, the A in the instruction means that it's using the generic key A, and but that register is not, let's say, accessible at normal execution level. You need to be like at not hypervisor, but not normal higher execution level. Yes, I don't remember now the name.
Yeah, but I think that's the idea is got clear. Thank you. I need to keep a look at the time, and we are 1 minute over time. So let me say thanks to all the presenters and to you attending this session. I would finally like to invite all the speakers and also the attendees to move on into the poster sessions, which belong to this presentations. They are located somewhere in Gallertown in the Bund, and over there you can follow up with additional questions and answers in the poster sessions. So